Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over carboxylic acids. Now you might be wondering, why are we starting carboxylic acids now, section 5, when the title of this chapter includes carboxylic acid, right? And if you're not wondering it, I'm going to tell you anyways. So normally you can pick where to put this topic, but the idea is that carboxylic acid is our gateway molecule. Now remember, everyone can become a carboxylic acid, and it can become everyone. But not only that, if you want to go into the class 1, let's say, so if you want to get into the class, not 1, but class 2, if you want to go into that world, which is that whole list of acyl halides down to amides, then in order to do that, from whatever you're coming in, your first step is to become a carboxylic acid. And then from there, you can go further into whatever you want. But when you start from something that is not a class 2, right? So if this is well, just anything. I'm not even going to write non-class 2. Just anything here that you have that you want to make into a class 2, whether it's an acyl halide, acid anhydride, whatever, you've got to go through carboxylic acid. So we think of carboxylic acid as the gateway. So this is the gateway molecule. The gateway molecule. Okay? Carboxylic acid. And it's for that reason. Everyone must go through it in order to become something else in the class 2 family. Alright, so now let's start by talking about several things. Now, we're not going to just learn about the reactions. There's properties to discuss, the acidity, a little quick review on that, and pH, preparation. How do you make carboxylic acids? And there's a whole bunch of ways to do that we have to learn. Okay, and they're pretty much review. And then we'll do the reactions like we've been doing before. Okay, let's get started by talking about properties. So the first thing is, let's talk about the boiling point. I'll just write it out. So boiling point. And so the carboxylic acids are roughly the same as alcohols in terms of boiling point. They're about the same. And the reason why is because they have the same idea, which is if you have, let's say, a double bond O with an OH, the thing that it can do is it can become a dimer, or it could dimerize with other carboxylic acids. And the way it would work is, let's say like the double bond O over here would be attracted to that H, and then you would have an O with an H right here, and then the R. So you see what I just did? I was able to take two carboxylic acids and put them in such a way that the H and the O and the H and the O are attracted, and look what it makes. It makes like a 3 on both sides, 6-membered ring here. Right? So this is very stable, right? So you could see how this right here would be hard to separate because it has hydrogen bonding in 2 different positions. Alcohols do something similar to that, except it doesn't make a 6-membered ring. So this right here is emulating a 6-membered ring. It's a dimer, and this really makes it pack well together. And then they start packing with others as well into 3-dimensional shapes. So that's what happens, and that's why the boiling point is roughly the same as alcohol. Now remember, alcohols had a better or higher boiling point than amines, which we'll come back to during the next exam. So amines, and then amines are better than halides, alkyl halides, right? So you have like alkyl halides over here. This is like last semester stuff, alkyl halide, and then you would have ether, which is around the same as hydrocarbon. Okay, I'll just leave it at that, ether, because this is going far back. So what's key here is that carboxylic acid and alcohol, they are at the top of our list, and everybody falls from there. Okay, and you could add aldehydes. Aldehydes are after alcohol, so you don't have to really go that far into it. It's not that necessary. What's really important to note is where carboxylic acid stands as being at the top and why. Here it is. Okay, now the other thing I want to remind you about with boiling point that you have to remember is the longer the R group increases boiling point. So if you have a carboxylic acid like this compared to like that, then this one has the higher boiling point. All right, and then of course polarity. So if you increase the electron withdrawing groups on carboxylic acid, that will increase the boiling point. So if you have a carboxylic acid like this, and let's say it has a fluorine here, and then you compare it to one that has, let's say, one fluorine over here. Actually, it doesn't matter where, it just matters the number. So let's say there's 2 here and there's only 1 there. This is going to have a higher boiling point. Okay? So having more polarity is going to increase the boiling point. And then finally, the last thing is what we talked about last semester. The less branching is best with hydrocarbons. Okay? So if you have a carboxylic acid like this, that's going to be better, higher boiling point than that. Okay? So this is best off. So this is a higher boiling point than having it branched. So branching reduces surface area. Surface area makes it easier to boil. So those are the rules that we have to remember from last semester in case it comes up on our exam. So for boiling point, it dimerizes, it makes this kind of 6-membered ring in this case, and you can have this happening over and over again with others. They pack well together. The longer the carbon chain, the better. Higher the boiling point. That's increasing van der Waals effects, okay? The London dispersion. And then as far as electron withdrawing groups, the more the better because of polarity. Increased polarity, increase the attraction, the dipole moment, right? So that's a dipole attraction. And then less branching is going to allow for better van der Waals, right? Because the surface area, if it's no branching, it's better than branching. Branching pushes them away from each other. Okay, so that's it. That's kind of the review I want to do with boiling point. Now let's talk about B. Let's talk about solubility. And that's the other property. So for solubility, what you have to note is that first off, in general, this is always true. Charges are always the most soluble. Charges are the best, positive or negative, okay? Then you have carboxylic acids, okay? So carboxylic acids are next up in the solubility trend. And now from here, of course, after that, you have alcohol and then other polar molecules, okay? These are the solubility trends that we look for. Now, typically, what we want to find are things that are positive or really partial positive, because solubility has to do with bringing something into the solution. So imagine this is an ether layer on top, right? This is ether, okay, ether, which is where it's a hydrophobic area, hydrophobic. And then over here in the blue, this is water, okay, this is H2O. So that's hydrophilic. So what happens is things that are charged goes into the water. Okay? They're hydrophilic. Whereas, and by the way, I mean area, hydrophilic area. And then hydrophobic area. Okay? So things that are not charged are going to go into the ether. Non-charged. Or actually, I should just, it really comes down to one thing, hydrocarbon. Hydrocarbon goes into the ether because they're hydrophobic. They're afraid of water. Non-polar goes into ether. Okay? So when you have charges, they're the best. They're going to go into the water. They're going to be soluble by going into water. Okay? And then carboxylic acid, alcohol, and then just polar things in general, like alkyl halides. The more halogens, the better, things like that. Okay? So now, as far as the carboxylic acid, I want to point out that let's say you have a carboxylic acid like this, and then you have one like this, and then you have one like that. Okay, so I just want you to see something. So if I ask you to rank them, increasing solubility, okay, here's an example. So the first thing is carboxylic acid, carboxylic acid, carboxylic acid, right? But this is the base form. So this one is the best. This is number 3. This is the most soluble. Most soluble. Why? Because it's charged. Charge wins over neutral. So these two are not charged, so they're not as good as this one. Now, the next one to figure out is between these two. Now, if you go by boiling point, this is why I want to show you this. The longer the carbon chain, the higher the boiling point. It's the opposite for solubility. Okay, so this is number 2. This is number 1. 1 is the least soluble, and 3 is the most. So notice the trend is a little weird, right? Because it's not like boiling point. This is what makes boiling point solubility different. They both want charge and polar, but what they don't want, the opposite, is the size.